Okay, so I tried to erase a little bit, but not completely destroy the diagram. So now we want to talk. We showed for the vertical lines it's the same.
Yeah.
Now we have to do the non-vertical lines.
Well, but for the horizontal lines, it would be the same.
Okay, what do you mean by that?
Well, you can do the same thing for the horizontal lines as you did for the vertical lines.
So like a line up here?
Yeah, because you could just rotate the axis and they become vertical.
How would I rotate the axis?
Well, actually, it becomes vertical, but on this side.
Okay,
or you
so
can flip it. You can flip the axis this way or the other way.
oh, interesting. I could take the horizontal lines and rotate the axis over here, right?
So that would probably become that point.
That would probably become that point. How many degrees do I have to rotate? Do you know? How many degrees do I have to rotate to make that line be a vertical line?
That's a right. I think that's a right angle.
Looks like a right angle, so I would have to rotate how far?
90 degrees.
90 degrees. That's interesting. So with horizontal lines, just by rotating, I could go back to my other argument. That's nice.
Yeah.
What about a line? What about lines that were 45 degrees? What do you think I could do?
Well, you'd have to rotate the axis 45 degrees.
Huh.
So
the argument stays the same. You just have to rotate the axis that number of degrees.
Interesting.
So
Do you think it works for any
yeah.
slope? Any slope?
Yeah, because you just rotate it that number of degrees.
You rotate it until it becomes vertical, and you go back to your other argument. So there's an amazing symmetry with the circle, right?
Yeah.
So these lines here, however I have to rotate them, are going to match up somehow
Because the circle has infinite symmetries.
with lines that come like this. Actually, did I get that right? No, sorry, I got it exactly perpendicularly wrong. With lines that go this way. Sorry.
Cool.
In the circle that go that way.
So it is the same.
Sorry, now I'm confusing myself. The horizontal lines went this way through the circle. And these lines, how do these lines go? Well, let's see, you rotate. And what are they? Oh, yeah, they're just passing through that direction like this.
Yeah.
Okay. And we do our 1/x trick. Sorry for that confusion. I got confused. So no matter what line we have, we can rotate it, match it with another line.
Wow.
So there's the same.
So does every line here go to a line over there?
Yeah.
Does every line over here come back to a line over here?
Yeah.
They're the same.
So it's the same.
Whoa.
Isn't that amazing?
Yeah, it seems like the circle is much smaller and the plane is much bigger.
But there's the same number of infinity.
Wow.
Now there's another surprising thing that I don't want to get into because it's a little harder.
Yeah.
But believe it or not, if we look at the tangent lines, oops, missed. If we look at the tangent lines, there's also the same number of tangent lines as there are lines outside or inside the circle. But that's a little bit more
That
difficult
looks a little harder.
because it doesn't. The argument we did doesn't work. If you look at the vertical tangent line here, there's only one of them, but there's infinitely many points out there, so the math is different
Yeah.
between them. But that's fine. We'll talk about that later, maybe when you're 25. Okay, it's a little harder. It's a very cool question you asked, and the math behind it has some really neat stuff. Rotating, infinities, maps going 1-to-1 back and forth. Pretty fun, right?
Yeah.
This is a neat topic and was a very interesting topic in the late 1800s, and that is why the mathematician Georg Cantor is really, really famous. Good job, guys. Great question. I'm glad we had a chance to talk about that.